Well, here we are for the second part of the second lecture, Lecture 2b. In this lecture, we're going to talk about heat capacity and reversible and irreversible processes. First, let's talk about heat capacity. The formal definition of heat capacity, remember in the last part of the lecture, we said that heat capacity, we just threw it out, had units of joule per Kelvin, sort of at an introductory level. Actually, the formal definition of heat capacity at constant volume is this. CV is how U changes with T at constant volume. All right, maybe you're not familiar with this notation. Here we have this symbol like this, whereas we've introduced, and maybe you're most familiar with the symbol like D, infinitesimal change. This also means infinitesimal change, but it means that there's actually more than one variable, and in fact you're taking the derivative with respect to temperature when in fact it depends upon two variables, temperature and pressure. Oh, something depends on two variables? That means we're talking about calculus of several variables. And where is there it is. So calculus of several variables. And let's talk about that. There's I think it's Math 223 at Binghamton University that concentrates on calculus of several variables, but you may have had an introduction to that in Calculus 1 and 2. Let's talk about one variable. We said, for example, we have a function of one variable, f of x. An example that will be a linear function, f of x is equal to mx plus b. You can also have functions of more than one variable. Let's look at two variables. You then would write that a function of, say, x and y. And a function of that mean f of x might be, say, m1 times x plus m2 times y plus b. So two variables, x and y, and given a particular value of x and y, you can then calculate the value of the function. If we just plot f of x on a graph versus x, depending what function it is, we'll get something like that. If we try to plot, this should be f of x and y, a function of two variables. If we try to plot a function of two variables, we'll need actually three dimensions. We have x and y. Those are our two independent variables, and our dependent variable will be the third axis where the function is calculated for some x and y. So this will describe that, and so on. For three variables, you need a four-dimensional graph to show that, and so on. Okay, so we're talking about calculus of several variables. Over here we can say the derivative of the function f of x with respect to x, and that is equal to, something you can calculate using what you learned in calculus. There we go, f of x. Over here, how do you talk about derivative of a function with respect to some independent variable? Here we just had one, it was unambiguous. Here, are we going to talk about the derivative with respect to x or the derivative with respect to y? That's where that simple partial derivative comes in. Partial derivative of f of x, y. Let's take it with respect to x. That means we're considering y a constant. So that's how you would write that. So this means you have a function that has more than one, as a function of more than one variable. So this means you're taking the derivative with respect to one of the variables and holding all the other variables constant. So when you take the derivative, just consider that as a constant. Similarly, you can write a derivative of a function of two variables with respect to the second variable. and holding the first one constant. So that's where that symbolism comes from. Now what does it mean holding, say, y a constant and take the derivative of x? Well, holding y as a constant means essentially you have some sort of plane here. I'm not very good at drawing a plane, but at a constant value of y, you will define a plane here, and projected on that plane will be f of x, a function of one variable, at that particular value of a second variable. So really you're taking the three-dimensional and slicing it up by holding one, and you're putting the slices perpendicular to the axes that you're holding constant to convert this three-dimensional into a two-dimensional, and then you look at the function right on this plane here and then take the derivative. So essentially that's what you're doing. This then is a specific case of the more general case where you're taking planes, slices out of the three-dimensional space. All right, so that's what that means. Now, writing it this way, we imply that U, remember U was the internal energy, or the energy of the system, is a function of two variables, temperature and volume. And we'll look at that more carefully later on. Okay, so we have U is a function of those two variables, temperature and volume. So we can take the derivative of U with respect to temperature, and I'm using this symbol because we have a function of more than one variable at constant volume, or we can take the derivative of U with respect to volume at constant temperature. So here we're taking slices through the v-axis, here we're taking slices through the t-axis. All right, and we're going to define this. We're going to define this as a heat capacity at constant volume. There's constant volume, there's constant volume. So how the internal energy changes with temperature at constant volume is the constant volume heat capacity. So if you think this number is very large, so you have a very big change with temperature at constant volume, then you have a large heat capacity, and so on. All right, so that's what that means. Now let's do an example. We'll learn in statistical thermodynamics in our 2 lectures at the end of the course that the internal energy of n moles in a monoatomic ideal gas would be approximated by, say, helium, is 3/2 nRT. What is the heat capacity at constant volume of a monoatomic ideal gas? All right, so we have the internal energy is that. So for a monoatomic ideal gas, the internal energy U is 3/2 nRT. 3/2 nRT. So what is the heat capacity at constant volume? Well, heat capacity at constant volume is the derivative of U with respect to T holding V constant. So the derivative of U with respect to T holding V constant is a derivative of 3/2 nRT. I should really be talking about partial derivatives. Partial means it's not a total derivative, but it's partial with respect to just one variable, with respect to temperature at constant volume. Note that volume doesn't appear in here, so we don't need to really worry about that. It really doesn't have to be a constant volume. So the derivative here with respect to temperature is just 3/2 nR. So that's the heat capacity at constant volume of a monoatomic ideal gas. All right, so that's the formal definition of heat capacity at constant volume. And actually we'll have a similar definition when we talk about enthalpy, heat capacity at constant pressure. But we'll have to introduce enthalpy first. We'll do that later on. All right, so that's that slide. We know what the formal definition is, and we did an example for monatomic ideal gas. All right, now let's talk about reversible and irreversible processes. You may recall in the first part of this lecture, we had an example of PV work where we reversibly took a state of a gas or a system of a gas from the state 2 liter to 1 liter at constant temperature. And that was a reversible step. So reversible, recall from that lecture, the change from initial to final state occurs by an infinite number of infinitesimal changes. So if we look at our example of PV work, here's our piston or frictionless piston, and let's compress the gas. So let's press down here, and we're going to do it in a series of steps to eventually going to say have the volume. So our first step is an infinitesimal step. Let's give this x. So the steps are dx, and if you do an infinite number, we will eventually have the volume, infinite number of steps. So it'll take an infinite length of time to get there. So it's an idealization. So reversible processes, in a sense, are idealizations. Now let's take the opposite of reversible processes. That's called irreversible process. Let's take an example of that using our PV work kind of thing here. And so here we have like this. Here's our piston, and say on here we have a certain weight. Okay, it's a weight, and that's pushing this piston down. Suddenly, in zero time, we remove the weight. So now suddenly the pressure has decreased just instantaneously from one pressure to another, and now the volume is going to change. In fact, the piston is going to go up, the volume of the gas or the system here is going to increase. So that's an example of a irreversible process. So the change from the initial to final state occurs by a finite number of incremental steps. In this case, it was just one step, and suddenly the pressure changed. All right, so why is this important? Well, sometimes you can calculate a change in a reversible process from one state to another, whereas it's more difficult for going from that same state to the same final state. It's more difficult to calculate irreversible processes. But however, remember, for certain things like internal energy, those are state functions which depend only on the initial and final states. So it doesn't matter whether you go from the initial to final state by an irreversible process or reversible process. For a state function, the change in the state function is the same. It doesn't depend upon the path you take. All right, so keep those things in mind. They'll especially be useful when we talk about the second law of thermodynamics. All right, let's look at an example here. Let's do two changes. Here's our initial state, which is some pressure. Let me change the ink color here to say black. So we have some pressure, some initial pressure and some volume here. That's our initial state. Oh, actually I wrote that, initial state. And then here we have our final state. We have P2 and V2, and our final state's like this. Now let's go from the initial state to the final state by two processes. First, we're just going to say dump a weight on here, so we're suddenly going to change the pressure and instantaneously. Then the volume is going to change. Here, we do it by a reversible process, going from here to here. Instead of just dumping a weight, we put an infinitesimal weight on here. So it goes an infinitesimal amount. Then we put another infinitesimal weight here. It goes an infinitesimal amount down, and so on. And eventually, with an infinite number of infinitesimal weights, you'll get to your final state. All right, so is the system's work larger in a reversible process? Here's the reversible process, or the irreversible process when you go like this. Okay, well, let's see if we can answer that question. Now, we reduce the graph on the previous slide right here. So this is pressure, and this is volume. Here's our initial state, here's our final state. So we're going to go down like this suddenly, and then go across here. So that will be our irreversible process. And let's try a different color ink for the reversible process. Let's try yellow. Of course, this won't show up here. And this then will be the reversible process. Note the reversible process is a smooth curve. Irreversible process is jagged. So which process will give us the greater amount of work? All right, let's go back to white. So recall that work is minus the integral of P dV. So a qualitative way of looking at this is the area, or say minus the area under a plot or a graph of P versus V. Because remember, integrals are summations. Essentially, when we talked about differentials, when you talk about integrals, you're summing over deltas, but in fact delta eventually becomes infinitesimal dV, and then you have the integral. All right, so let's look at the area underneath the PV diagram for this. There we go, something like that. So the integral of P dV for the irreversible process is like that. Let's look at the area. Let's do this yellow for the reversible process. Ooh, we get lots more area under the curve for the reversible process. So the reversible process, more work. So if you're looking at trying to get some work out of a system or do work on the system, you can get a lot more work by going by a reversible path, or as reversible as you can make it, rather than an irreversible path. Okay, so that's it for the second part of the second lecture. I hope you enjoyed this. This lecture and the first part of it should be viewed by the time you come to class on Friday. All right, so, ignore that. Have a nice evening or morning or afternoon, depending on when you're looking at this.